Recon is mass heat and momentum balancing software with data reconciliation. Recon is comprehensive interactive software for modeling of complex chemical and power plants on the basis of measured or otherwise fixed data. Recon does mass, energy and momentum balancing, thermodynamic calculations, etc. It is designed primarily for the validation of data, which has been obtained from operating processes. It can be used also for simulation of plants' behavior under changed conditions. Recon can be also used for classical balancing in the stage of the process design. Recon can be used in two operating modes. Data reconciliation and validation mode is used for models solved on the basis of measured or otherwise set process data. Measured should be flows, temperatures, pressures, etc. Redundant data are reconciled, unmeasured process variables are calculated, and model parameters, such as heat transfer coefficients, efficiencies, etc. are identified. Simulation mode is predicting plants' behavior on the basis of models identified in the preceding data reconciliation and validation mode step. In practice, Recon's operation can be switched between these two modes. It is suitable for updating models and using them for predicting plants' behavior, optimization, or answering what-if queries. Recon can be used to treat measured data before its further usage for other purposes, such as simulation, optimization and control. The whole data processing is shown on this figure. Inputs are measured variables, known constants, mathematical model, and a model of errors. Model of errors is determined by precision and accuracy of measuring instruments. Engine for data reconciliation is in our case used program Recon. Outputs are reconciled and estimated values and other information such data quality, confidence intervals, etc. Recon can solve tasks of different complexity. For example, model of heat exchangers for crude oil preheat, up to complete industrial plant. Typical tasks solved by Recon could be mass and energy balances of chemical and refinery plants, natural gas processing, distribution systems of utilities, detailed balancing of chemical plants, monitoring industrial heat exchange systems like crude preheat trains and similar systems, balancing steam systems, monitoring and online thermodynamic analysis of power generation systems including turbine efficiencies, low and high pressure preheats, condenser heat transfer, etc. Combustion processes, such as industrial furnaces, coal and gas-fired boilers, balancing water treatment, like softening and demineralization in power plants, power and heat cogeneration systems including seawater desalination plants, flow of liquids and gases in pipes, and pipeline systems including their hydraulics, detailed mass and energy balance of nuclear plants, including primary and secondary circuits, and advanced assessment of nuclear reactor power. Models are created in graphical user's interface. Besides that, the user-defined equations are available. There are three kinds of them: data pre-processing, model supplements, and data post-processing. We will show them on small model of steam cycle. Users-defined equations are accessible from menu, accessories, user equations. There are all three kinds of them. Data pre- and post-processing enable enhancing model by new results without enlarging the model proper. For example, to add some KPIs, process economy calculations, etc. Model supplement are equations enlarging model's redundancy by one. Basic editor for writing new model equations contains standard mathematical functions, logical expressions, task variables used in model, physical properties of streams, and various models, such as calculation of turbine efficiency, heater's log mean temperature difference, etc. It is possible to use in equations complex thermodynamic functions, physical properties, etc. User-defined equations can be used also for defining model inequalities. In Recon can be also solved problem of chemical reactor. Chemical reactors can be modeled by two ways. The standard method uses chemical reactions, with stoichiometric coefficients, stored in Recon's reaction bank. Sometimes reactions in the system are not well known, for example burning of coal. In this case user can use the second method, based on the so-called reaction invariant chemical reactor. In this case only the knowledge of atomic composition of components is required. In this model of coal boiler, the coal input stream is defined by concentrations of each components, such as water, ash, and flammable part. Atomic composition of components are further defined in list of components on the right side. For example, water, carbon dioxide, coal. Recon has also built-in tool for gross errors treatment. Generally there are 3 steps. Detection is finding the gross error presence. The data quality is continuously monitored via the status of data quality. This variable should be under normal situation below 1. Values above 1 signal the presence of some gross error, either an instrument or model error. Status data quality is based on so-called global chi-square test, testing the value of the least square function minimized during data reconciliation. Recon detects gross error by running every calculation. Presence of gross error is noted, and in the list of results we can see status above 1. Second step is gross error identification. There are several methods available. Values of normalized adjustments. Suspect measurements are those with the highest normalized adjustments. In Recon such flows are marked in color on the flow sheet. Successive elimination of suspect measurements. In Recon we can find suspect measurements via menu, calculation, gross errors. Suspect variables from the step 1 are automatically set one by one as unmeasured. Variables with the largest decrease of status data quality are suspect. Values calculated in the step 2 are compared with limits set on variables. If the calculated value is not probable or feasible, this suspect is excluded from the set of suspects. In the case of mass balance, the imbalances around individual nodes, or their combinations, can be statistically tested. It is called nodal test. Streams around suspect nodes are suspect. This method is suitable also for finding the frequent model errors, such as leaks, or neglected mass accumulation. Covariance matrices of adjustments are available for detailed analysis of the gross error identification problem. The steps in gross errors identification are semi-automatic. All this serves as a decision support system for the user. Recon also contains Monte Carlo simulation module. It is accessible from Manu, Calculate, once the model is calculated. Monte Carlo is based on repeated simulation of the measurement process. Individual measured data sets are generated by adding random errors to the base case data. In this way real measurement is simulated many times with the following data reconciliation. In Recon the size of random error is set up by perturbation factor. Results can be statistically evaluated and compared with theoretical values. In this case we can see 4 simulations, with status data quality above 1, marked by exclamation mark. The higher the generated random error will be, in Recon called perturbation factor, the more simulations with gross error will be. Using this simulation, we check the model robustness and tolerance to random error measurement during calculations, which can lead to divergence of calculation. Recon enables one to create reports in the MS Excel environment. The solution is based on Excel templates prepared by users. These templates contain links to Recon's database. In this way any user can define unlimited number of report templates which can be later used for generation of reports. The complexity of these reports is limited by Excel's capabilities only. Reports can be generated either in the interactive way by a user or automatically at a predefined time. Thank you for attention and good luck with Recon's modeling and data reconciliation. For more information and documents visit our website chemplant.cz.